Hello everyone, I'll be doing my EM3 assignment presentation on Euler method in approximating the solution of IVP. The definition of Euler's method is, it is a numerical technique for approximating the solution of an ODE with a given initial value. It uses the gradient of a derivative of a known point to estimate the value of the function at the next point. The formulas used in Euler's method is quite simple. It is xn equals to xn minus 1 plus h, where h is the step size. Xn is the value of x at the current point, and xn minus 1 is the value of x of the previous point. To find y, is yn is equivalent to hf bracket xn minus 1 comma yn minus 1 close bracket plus yn minus 1, where yn is the current value of y, and f xn minus 1 comma yn minus 1 is the derivative at the previous point, where and h is also the step size. So for example, we have dy dx, which is equivalent to 5x log 5, where y0 is equal to 1 as well, which means yx is equivalent to 5x. We assume that the step size is 0.25 using Euler's method. So the table below shows the calculated values, and in comparison, you can see the value of yn and the actual y. As you can see, the values are quite similar, 0.7 in value apart from each other, which means this is an accurate way of approximating the value of the actual y. If we compare it to the graph below here, we can see that the actual value of y equals to 5x is a smooth curve, whereas using the Euler's method, the graph has a few points of inflections, which means that there's sharp turns from here. As you can see from here, there's a sharp turn to here, and so forth. Based on the given information, we know that x is 0, y equals to 1. And we can find the gradient at this point, as they've given us the formula over here. So we can just plug in the values, and we will get x, our gradient, to be 1. So for the following rows, as our step size is 0.25, x will also increase by 0.25. And we can find our y new by using the formula yn minus 1 plus h times your previous dy dx, which is over here, can be simplified into this. So I take the previous y, which is 1, and I times it by the h times the dy dx, which will give me 1.25. And for the new gradient, I can do the same thing and just plug the x and y values over here, which will give me this. And then I'll repeat it down the row, which I can do with just Control D, and it will give me all the values over here. And I can repeat the steps also for the following step size 0.05. But there will be more values, as 0.05 is a smaller step size than 0.25. Hence, there's more numbers counting towards 1. To compare my approximated value to the actual value, I've actually done the calculation to find what the actual value of y is when x equals to 1. So what I've done here is dy dx is equal to x squared plus 1 over y, and I have split it, the dy and the dx, to one side each, and have integrated it. And afterwards, I found the c by substituting y equals to y, x equals to 0 to find the c. And from there, I could find that y is equivalent to square root 2x cubed over 3 plus 2x plus 1. And from there, I substituted x equals to 1 into the following equation to be able to find my y, which is square root 11 over 3, or 1.91485. And to compare with my approximated values, when my step size is 0.25, the difference in value, the error, is 0.00563. And when the step size is 0.05, the margin of error is 0.00192. This shows that when the step size is smaller, the values are much more accurate. Hence, when doing Euler's method, it is better to use a step size which is smaller. Thank you for watching my video on my EM3 math assignment on Euler's method to find the approximation solution of the IVP. I hope you found this video beneficial. Thank you.